is Peter Chen from Columbia, and he's going to talk about file reduction for material point methods. It's leveraging deep learning. So Peter, please, the floor is yours. You have 20 minutes, and I'll let you know. And trying to save 5 minutes for questions if you can. Thanks.
All right. Thank you for the introduction. This is Peter. I am a PhD student at Columbia Computer Graphics Group. And this is a joint work with Maurizio Chiaramonte from Facebook Reality Labs, Eitan Greenspoon from University of Toronto, and Kevin Kohlberg from Facebook Reality Labs. High fidelity physics-based simulation, as you guys all know, has become indispensable across a wide range of applications in science, engineering, and entertainment. As we rely more and more on these simulations, greater demands are being placed on simulations with extremely high spatial temporal resolutions, which unfortunately incurs a very high computational cost. Very often, we find ourselves in a situation where the simulation we want to run is just too slow for any meaningful application. An ideal simulation would run in real time, and even beyond real time. Maybe just 5 years ago, and if you can get your simulation running real time, you'll be like, man, job done, let's go get a beer. But these days, with the rising need of using simulation as a tool to generate data for reinforcement learning, real time is not even enough. So how do we go from weeks to beyond real time? Lots of great works have been done, for this endeavor. And the work I'm presenting today is just, trying to make this happen. And in particular, I'm interested in using this model reduction / machine learning approach. Let's ground ourselves in a particular application that requires physics simulation, virtual reality. In this video, the user is playing the Jenga game virtually. The reason that this game is possible is that Jenga blocks are being physically simulated as rigid body, stacking on top of each other. However, current approaches are often limited to rigid body dynamics because of the real-time requirement of the simulation. What if we want to manipulate something like super Armstrong, which is super elastic and super nonlinear? And what if the object we want to play around is a two-space, which has some complex nonlinear elastoplastic behavior going on? So we need a more robust physics simulator that can simulate the complex motion of the two-space in real time. Well, there's a particular numerical technique that's very good at simulating these large deformation effects, the material point method, or MPM. MPM was originally invented by Salsky et al. In 1994. It was designed as a way to extend the popular fluid simulation framework, the particle in cell method, into solid mechanics. It is essentially a method to solve your momentum balance equation by discretizing in space and in time. Recently, I guess 8 years ago, not so recent, it was made popular in the computer graphics community due to its usage in Disney's snow simulation in Frozen. MPM can simulate your sponge with no problem. MPM can also simulate the two-space quite well. And also, granular materials like sand. It can also easily handle phase changing, such as lava, melting a bunny, melting a chocolate. So let's have a high level idea, understanding why MPM works so well for these applications. In the numerical analysis world, there are typically two types of discretization philosophies. The Lagrangian way of discretization, essentially discretizing the material, which makes it a good candidate for solid mechanics. And the Eulerian way is discretizing the space, which makes it natural to model fluid mechanics. but neither is suited for unified treatment of solid and fluid with extreme deformations. And what makes MPM special is that it is a hybrid Eulerian Lagrangian approach that adopts the Lagrangian view for kinematics tracking, while adopting the Eulerian view for solving dynamics. Therefore, it is able to combine the best of both worlds. It's a single simulation framework that can model both solid and fluid and everything in between. However, because it adopts a dual representation of the material, it is, as you can imagine, is like basically at least 2 times more expensive than the others, right? It is computationally more expensive than the purely Lagrangian approaches or the purely Eulerian approaches. Therefore, we want to explore model reduction for MPM. To begin, MPM represents the continuum as a finite set of material points. These material points here, they shouldn't be considered like individual particles really, but they are individual particles. Rather, they represent a discretization of the original continuum. Each material point stores kinematic information, namely particle mass, position, velocity, and deformation gradient in the case of elasticity, because you need this deformation gradient to compute your stress, from whatever linear or nonlinear constitutive law you would like to use. And each step of PM proceeds as follows. And the first step is listed here. We have this collection of material points that represent the current state of the continuum. MPM then transfer these kinematic information of the Lagrangian particles to the Eulerian grid, like shown here. And after the transfer, we have this Eulerian description of the equation of motion, including the internal force and the external force. And these forces, are computed from the divergence of the stress, which again is computed through the Eulerian basis function. And on this grid, we can then, use this force to update the velocity on the grid. And after we obtain the new velocity on the grid, we'll then transfer this information, back to these Lagrangian particles. So we'll have new Lagrangian, new particle velocity and also new particle deformation gradient. And then we update the particle positions according to this new velocity, which is computed. And in the end, the material is at a different state than before. And note that the background grid is never really moved. It's returned to the uniform case at every time step. And to apply model reduction, essentially, we have to handle how to handle these kinematic information, as well as handle this dynamics evolution. In the first step, we need to build a kinematic approximation. A naive approach would directly construct a low-dimensional manifold for the discretized material point positions, right? So discretized material positions. And classically, people use linear subspace for constructing this manifold, POD or PCA. And more recently, people have been looking into using deep learning to construct this manifold, which has shown to be a significant improvement from the previous linear PCA approach. However, though, for MPM, in addition to the position information, we also need the deformation gradient information. Then you'd be like, okay, then in that case, just build another, separate manifold that maps your x hat to your deformation gradients. Well, we're tempted to go on that approach, but we ended up deciding to take a whole different route. And so instead of learning the positions, we chose to learn the deformation mapping, which is a function that maps from the reference domain to the deformed domain. In other words, instead of constructing a low-dimensional manifold for a finite number of material points shown here, we're constructing a low-dimensional manifold for the deformation mapping, which is a function that can map infinite number of material points from its reference domain to its current domain. Consequently, we can readily obtain the other kinematic information associated with the deformation map. but just taking the derivative of this low dimensional manifold. For example, you have velocity, and also have the deformation gradient. And we can do this, again, for arbitrary material points in your reference domain. So let's write down this formally. Define the deformation map phi as a function that maps any point in the reference domain, shown here, to a point in the deformed domain at time t. And now let's introduce the approximated deformation map. What makes the approximated deformation map phi tilde special is that it is kinematically constrained. So the image of phi tilde is now constrained to be the image of G, where G is what we call the manifold parameterization function. So with this architecture, essentially, we're able to compute the deformation for arbitrary big X in your reference domain. And as a result of that, during online simulation, we can arbitrarily up-res or down-res our simulation, because whenever we need to add a point, we can just get its reference domain position, and then we'll have all the other the kinematic information that we talk about here. So now let's get into the nitty-gritty of training this neural network to approximate this deformation map. Given any simulation sequence, you will have the data of the position of each material point at each time step. So I here, varies from 1 to p, where p is the total number of material points, and which, for each material point. And then n varies from 1 to big N, where n is the total number of your time steps. And the total number of data you throw into your training, essentially p times n. Notice the double summation here. And this training loss is saying that we want to train the function g to be able to approximate the actual deformation map phi, which is a function of the initial material point position and time. In addition, there's another penalty term here. We also want to constrain the gradient of g to approximate the gradient of phi. And what we are optimizing here first is the variable theta, which is the network weights, which is pretty standard. But at the same time, we're also optimizing this generalized coordinates x hat. And for each time step n, we have a corresponding x hat that's uniform across all the material points. And since we're training this x hat while we train the network, there's no need to explicitly train an encoder, which is never used in an online ROM simulation anyways. And here are some training details. We're just using very simple structure right now, multi-layer perceptron, few layers. And for activation function, we're using the elu function, which can be viewed as a continuously differentiable extension of the more popular ReLU. We can't use ReLU because it doesn't have these smooth properties that we need because we have to compute the gradients of the network. And the other things are just pretty standard. Okay, so now it comes to the second step of ROM. Here, with this kinematic approximation in hand, we want to solve the dynamics of the generalized coordinates. So let's revisit the MPM algorithm. Since the deformation gradient information is available from the approximated deformation map, we no longer need to evolve the deformation gradient explicitly. And to evolve the generalized coordinates, we can follow the standard ROM approach by doing a time discrete least square projection so that the generalized coordinates can evolve as closely as possible to the true dynamics predicted by the MPM solve. And in order to get any computation safe, we adopt a hyper reduction approach by doing the least square projection instead of have the summation going over all the material points. We only do this projection small subset of the material points, which is the set I. And just to visually get an idea, what does the hyperreduction mean? On the left is a simulation, the full simulation that consists of 30,000 material points, right? And on the right are the 23 points in the subset I where we use for least square projection. So just by computing the dynamics of only these points, we're able to, drive the whole 30,000 point simulation. Obviously, in general, one can solve a combinatorial optimization problem to pick sample material points, that give the least square projection error. In practice, for now, we just, choose these points randomly as shown here. In particular, we can sample densely on the boundary of the object where we especially want high accuracy. Let's now go in details on how to update the velocity, for the sample material points that we need to solve. Let's say this red point is one of the sample material points. Assuming a linear basis function, to accurately solve for the dynamics of this point, you'll need to compute the velocity, the new velocity on these 4 grid nodes. And to actually do first update on these 4 grid nodes, you would in turn have to include the information of the material points in all the nearby voxels. In 2D, that would be the material points from these 9 cells, but no more. So this is pretty nice because the solver only need to, look into the, local information here. It's not completely local, but also not crazily not local. However, in general, though, to find the material points in these 9 voxels, you would have to track all the material points so that you can know which one is, in the neighborhood. So this makes our, algorithm ON in the worst case scenarios, where n is the number of material points. Though the average case complexity can be lower, but still, this is not ideal. Can we do better than this? Can we bypass the need to track all the material points? Recall in the MPM framework, each material point is, it actually really serves 2 purposes. One is it is Lagrangian, the other is it is quadrature points. It is Lagrangian because these particles follow the deformation of the material and therefore effectively serves as a tracker of the shape of the material. And simultaneously, these material points are also quadrature points that facilitate these stress integration. So alternative to using these Lagrangian quadrature points for stress integration, we can also achieve stress integration to Eulerian quadrature points that discretizes space instead of the material. And since the quadrature point is Eulerian, we know its current position small x, and to get its initial position big X, we can invert the deformation map that is approximated by the neural network, and by doing a simple nonlinear solve. And then we can readily obtain other kinematic information from the approximate deformation map. Again, I want to stress that the key reason that we can throw in this Eulerian quadrature point on the fly is because we have this approximated deformation map, which allow us to obtain the deformation information at any point and at any time. With this Eulerian quadrature point formulation, our algorithm is now completely OR, where R is the dimension of the generalized coordinate. And here is an elastic cylinder under the gravity load. The full order model has over 1,000 material points. The reduced model has a generalized coordinate whose dimension is 5. And similar geometry as before, here we poke the tip of the cylinder, and the cylinder undergoes quick motion and recovers later on. This plot shows the effectiveness of hyperreduction using just a little over 10 simple material points. We're able to get a less than 1% error, which is on the same level as using over 1,000 sample points. And if we increase the poking data set dramatically to include simulation that poke at different directions, then during online ROM simulation, we can poke the reduced model continuously at different directions. Next, we look into the cylinder torsion and tension setup. The reduced model is able to capture, both slow and fast rotations. Now let's go into a larger example. Even with 30K material points, our simulation still runs in real time. And after training on the previous example, we can continuously manipulate the cylinder, such as rotating back and rotating up again. And here we compare the computation cost of the full order model with the reduced order model. The computation cost shown here is the work clock time for every physical second of simulation. And as you can see here, the reduced model offers, you know, 1 to 2 times, 1 to 2 orders of magnitude speed up, depending on the number of cores being used. And the reduced simulation runs in real time, you know, with just 1 CPU core. That being said, the neural network computation of the reduced order model is conducted on a GPU, and everything else is on the CPU. In the future, we intend to conduct a comparison analysis with full GPU treatment for both the full order model and the reduced order model. And for future work, we want to, you know, do multiple objects, you know, handling collision, which is a, you know, big advantage of the NPM, and also handling plasticity, where we have large flows, and also handle fracture, which will be discontinuous. We'll have to change our framework a little bit. And we also, you know, want to extend our, you know, our deformation map approximation techniques to other continuum mechanics-based discretization methods. You know, we started out, you know, designing this framework, the model reduction framework for NPM only, but, you know, we realized, you know, actually the deformation map approximation technique is really can be used for any like continuum mechanics-based discretization that, you know, use like a deformation map, you know, description. And we think this will be, you know, very helpful for, you know, in the future designing like multi-discretization frameworks that, you know, can benefit from this model reduction techniques. And lastly, you know, temporal reduction, you know, like in this work, we only presented like the spatial reduction essentially. You know, like in the previous talk, in the past days, you know, we talked about how, you know, people can use, you know, different, you know, LSTM, you know, or RNN or like neural ODE to speed up like the temporal, the solver dynamics. In summary, we proposed a first order model reduction attempt for NPM. The kinematic approximation is done through learning the deformation map, and the dynamics are solved through least square projection. With that, I would like to thank you for your attention. I'm happy to take any questions.
Yeah, thanks, Peter. We have time for a couple questions. So I guess I like the second approach is nice, right? Because you're using Eulerian quadrature, which you can say something rigorous about in terms of approximation accuracy. Do you add, so that's certainly nice. Definitely like when you're doing fluid problems with Eulerian Lagrangian, I've seen that be important. But then there's an issue in terms of resolution around fronts or areas that are dynamic. Have you looked at adding quadrature points or updating, you know, the sampling around areas where you might see, you know, high activity with this?
Yeah, precisely. I think, you know, like this idea of approximating the deformation map, you know, is really trying to approximate something that's infinite dimensional. So because of that, you know, you can essentially do it like a opera sample as much as you want. Yeah. So it certainly, you know, will be interesting to study problems where that becomes important, you know, like with large flows. So we can do, you know, adaptive quadrature points.
And so I guess, you know, like you said, the key is G is the training for G. When your network was really simple, did you see any pathologies? I mean, is that an easy training problem, or do you have to be careful about what, you know, how you do that, your points as you sample? What's been your experience so far?
Yeah. I think this training this thing, you know, is pretty straightforward in the sense that you just have to have enough computation power and let it run. But I certainly find to training this thing is harder than training, you know, the kind of like the classic approach where you just map your X hat to a finite dimensional number of points. So it takes longer. Yeah, but I didn't like, it wasn't like, you know, as long as you have the computation power, you know, I didn't see that to be like a challenging thing.
Okay, I think Carlos asked a question in the chat. It's like, he asked, would it be possible to work directly in a graph that takes the particles as nodes to avoid transformation from the regular grid? I think Kevin answered that in the chat.
I can quickly comment, and
Yeah.
Peter, feel free to chime in there. But I think that idea would be pretty similar to this idea actually that Peter has on the slide right now, where if you're generating like a prediction to any finite number of points, whether it's in just like a list as in a vector or in a graph format, the issue there is twofold. Number one, you can't easily get the deformation gradient out of that, which is like kind of critical for continuum mechanics. And the second is what Peter alluded to with the Eulerian quadrature. If we don't have the ability to predict continuously the deformation at any point in the reference domain, you can't sort of auto-populate a good Eulerian quadrature rule around potentially fronts that was just kind of discussed by Matthew. So that's sort of that whole idea of mapping from a low-dimensional vector to a high-dimensional vector is actually kind of an issue in these continuum mechanics applications for those reasons. Peter, do you have any additional comments there?
Yeah, no, I think, that also, I appreciate your question, Carlos. I can interpret your question in many ways. I think the way I interpret it is, like there in MPM, there's this like particle to grid transfer that's happening quite frequently. And as a matter of fact, that is indeed the bottleneck of the original MPM simulation. And I think it would be interesting, like how, essentially, creating some type of kernels, right? I think that's your idea to kind of, so that we don't have to do like this kind of, transfer.
Okay. Well, I think we're pushing up into Jan Felix's time. So thanks again, Peter.